1840 or something like that, is we're just going to talk about the most general idea of telescopes and what they do in the broadest sense, because, again, we have the entire electromagnetic spectrum that we're interested in, and the mechanics and the engineering of how you collect and trace X-rays and gamma rays back to their source versus infrared and visible light is wildly different. So I'll show you some telescopes, and there's no way that you would have, outside of being in this classroom, you probably wouldn't have guessed that they're telescopes. So summary is, how do they work in the most broad sense possible? The role of the Earth's atmosphere, which can be good or evil. Most importantly, and huge breakthrough probably at the beginning of your lives, is telescopes in space. Don't realize what a revolution this was because you were either not born or 1 year old when it happened. And then telescopes for every part of the spectrum and what they see and, kind of where they need to be. So this is, I guess, an iconic image of astronomers, like a lonely old man on top of a hill. I think that's, I don't know. It's actually not pointing up, so maybe this is a pervert. But this is not true anymore. So I'll show you an image of Edwin Hubble, like this famous Time magazine picture. He was basically the last person to do this. So many things are not correct. So you should get this image out of your head, whatever. You thought about astronomers hanging out on the tops of mountains and looking up and contemplating the cosmos. So why do we use them? And this answer has also kind of changed in modern times. So what do you actually use a telescope for? Its role is to do what for you? I should plant somebody in the audience to give me the wrong answer. Okay. So the reflexive answer, and this was true in the time of Galileo, and this is true up until like 1860 with the advent of photography, is that you want to make things that are far away look bigger, apparently bigger. So you literally look through the telescope and it appears bigger to you, and you're like, well, that's really nice, thank you. Do we need telescopes to make things look bigger in the year 2016? No, because I can just do this. Hey, look, it's bigger and bigger still and smaller and bigger, right? And even in 1870, you could do this. You could take a photographic plate and you could shine light through it and you could blow it up and have it cover the side of a building. And you and your friend could stand there and you could like totally, geek out on the particular craters of, this is for Vesta. So this is a really nice image of a rather large asteroid. So they do not magnify things. What's that? Yes. So what do we need telescopes for? It is this. And you can break up the jobs into two different groups, which seem like they're really related, and there's kind of a one-size-fits-all answer for them, but it's not necessarily true. Sometimes you care about your failure at job number 2 and have different ways of addressing it. Sometimes you care about your failure at job number 1 and have different ways of addressing it, depending on what you're looking for, how faint it is, how far away it is, or how much exactly resolution you want. But the two jobs of a telescope are, and there are different times when you want to do different things, is 1, collect as much light as possible, and 2, trace it faithfully back to the origin, so wherever it came out. And you can be good at one and not good at the other independently. So in particular, many of us share this problem, is what is the adorable creature here really good at? Job 1 or job 2? Yeah, this thing lives in a very low light environment, so it has really big eyes and big, at least comparatively big light collecting areas to do a really good job of number 1. So collect as much light as possible because it's nocturnal. And what is the adorable creature in picture number 2 really bad at? It's probably not true. I bet they're like fake hipster glasses. Glasses represent a failure to do 2, to faithfully trace the light back to its origin. So all of us who wear glasses have, stigmatism, like a defect in the eye, or, we just don't really have the shape of our lenses doesn't agree with the shape of the rest of our eyeballs. So we fail at job number 2. There's nothing wrong with job number 1. They're very different things. Okay. So job number 1, there's really no way around it. The only way to be successful at job number 1 as a telescope is to have a large light collecting area. And remember, we're every part of the electromagnetic spectrum is fair game. So this is a large light collecting area for the Mauna Kea telescope in Hawaii. It's an 8-meter mirror. So people have fabricated this 8-meter in diameter mirror. And I don't know how sick of you guys are of analogies, but if you were to blow this mirror up to the size of the continental United States, the defects in it are good to within like no more than a couple of millimeters. So exquisitely manufactured, carefully polished. The group of people who make this type of mirror, there's only one group in the world. The fabrication lab is underneath the football stadium at Arizona State University, which sounds like a really dumb place to put it, but apparently that's where it is. And there's one like family business in the North Island of Japan that supplies them with their special beryllium doped glass. So this is good. People work really hard for this. And then this is Arecibo. It's built into a natural depression in Puerto Rico during the 1950s when people actually spent money on grand projects like this. It's 305 meters across. That would be like 3 football fields. It's tremendously big. And this collects radio waves, so it just passively goes along with the drift of the Earth and sees whatever it is that's basically overhead. And there's no way around it. This is how you collect a lot of visible light and then radio light. So not much to say about that. Job number 2 can be really sticky because as well as just how carefully crafted your mirror is, there's actually like a fundamental physics problem with tracing light back to its origin. And this is the fact that light is a wave, and wave does funny wave-like things. So if light was really like truly a stream of bullets, all you have to do is, keep the bullets from deflecting, maybe in the atmosphere or something like that, and you can trace them back to the origin. But there's a different problem with light in the fact that it being a wave, if you try to squeeze a wave through a narrow opening, it spreads out. So this is called diffraction. This is an example of diffraction in water waves, is the water waves are coming through this channel, these 2 separated little inlets, and you can see them diffracting and spreading out and not being able to be traced back to their source. So if you're sitting there and really locally just looking at this water wave, you'd see like, oh, it came from there. And if you were sitting there and you traced it back, you'd say, oh, it comes from there. So this is a big problem in this little inlet if you wanted to figure out where the waves were coming from. Imagine that you have this little angular error and you're tracing it back like 100 billion or 10 billion light years or something like that, something really far away. So this is a huge bummer. And the figure of merit for whether or not you have diffraction of light waves is the ratio of the wavelength to the aperture of the telescope. So for visible light, it's usually not a problem. Visible light is, 100 billionth of a meter or something like that, and you have an 8-meter mirror, no problem. That ratio is many billions. But for radio waves like Arecibo, this is actually a big problem because radio waves are meters. And even with my absurd 300-meter dish, my ratio of wavelength to diameter, the amount of light collecting area, this is more like 300, and this is not good. So, yeah. Probably. This is, I would suspect if there was like an iconic radio dish that gets kind of like put into the backdrop of things. This is one of the few passive radar dishes in the world, I think. So there's really only one Arecibo. It's also featured in Contact, which is a little bit cheesy, but I don't know. It's got Tom Skerritt in. But yeah, I would suspect it is. I don't know. There aren't too many things like this. What's that? It's a scientific instrument. Or it's, El Radar and it hides mystical military secrets. I don't know. It's where they tuck the aliens they found.
It's not totally
Yeah. Hide all sorts of nasty stuff under Arecibo. I don't know. So for radar, this is a problem. For visible light, there's a bigger problem that swamps angular resolution. So we need a sneaky trick. Sometimes we'll use it for infrared and visible, but mostly we need the sneaky trick for long wavelengths like microwave and radio. I'll say that you this picture aside, you guys know about diffraction from one part of your life, is that this is turning what astronomers think is a bug into a feature. Is what type of sound comes out of that thing? Treble. What comes out of that thing? Bass. You have earbuds, right? Like, you don't need large things to create bass. You just take whatever membrane it is and vibrate it more slowly. Why is it that these are small and you can allow that one to be big and therefore really well manufactured and really high fidelity? Well, wavelengths of sound are, bass sound would be maybe like 5 meters or something, and treble sound is shorter, so higher pitch, shorter frequency. So you actually have to pass the shorter frequency wavelengths through a smaller opening because you want it to diffract. What you would hate to have happen is you play high frequency noise or sound, whatever, and it doesn't diffract and it comes out in a beam. So you have to be standing in a particular location in the room to hear it. So the reason these are smaller is because you actually do want to squeeze the sound, the wave, and have it spread out. So these are actually forcing diffraction and forcing them to be room-filling and spread out. And if you played really, really high-frequency sound out of a speaker like this, it would just come out in a straight beam. Something that astronomers want, something that people who want to listen to music and not one particular slice of their room don't want. So it's something that you know about from elsewhere. So we have a trick that has nothing to do with job number 1, even though it might look like it, that addresses job number 2. And also kind of iconic astronomy images are things like this. This is the really uninspiredly named Very Large Array. It's a very large array of radio telescopes. And then this is this twin set of telescopes also on Mauna Kea, on the top of that Hawaiian volcano. And they're an array. And what they do is they get light from different aspects, and they compare the light, and they try to fix the angular resolution problem. So by taking multiple samples and agreeing upon them, what they're able to do is actually act like an effective, larger dish that has the angular resolution of this, even though it's collecting light in that area. So if you spread out all of the telescopes in the very large array to their maximum extent, it basically has the angular resolution of the whole thing, even though it's just collecting the light within the dishes. So there's a trick. A little technical, but there's a trick. And if you see something like this, or even more absurd, is now that we live in an era of fiber optics and instant communication, this is the very, 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 very large array. It's not what it's called. Is that there's a radio telescope in Chile and a set in Arizona and one in Hawaii. And they're acting as if they're a single radar dish of radio telescope of basically the radius of the Earth. So this thing has the angular resolution to read pocket change on Mars. It doesn't have the light collecting area to do that, but it certainly has a resolution. So this thing can look at radio signals that are really, really far away and pinpoint their size to a very, very incredible degree. So this trick needs to happen instantaneously. So what you can't, so the reason that, Hubble orbits because we couldn't get it to not orbit. But the trick of Hubble's orbit is that it's always facing away from the sun. So it can do something that no ground-based observatory could possibly do, which is stare at the same location in the sky for an indefinite amount of time. But you actually need simultaneous dishes to do this trick because you really have to compare the light to each other instantly. So there's a limit to this, and there's so that thing is what's called the Rayleigh limit, if you have been through Physics 223 or will here, is that has to do with I pass light through some aperture and it'll spread out, diffraction. There's another problem is that the atmosphere both absorbs and the atmosphere distorts. And we're really grateful for the fact that the atmosphere absorbs, namely things like X-rays and ultraviolet light. But for astronomy, especially now that we want to do things in every single wavelength, there's a problem. And we would like to get all of the light, and we would like to have it come through without being molested. And this is a diagram that indicates basically how far, we'll call it 90% of light travels before 90% of it gets absorbed. So gamma rays actually get attenuated. We're really happy about that. X-rays don't make it through most of the atmosphere. Ultraviolet light, we're very grateful for that too. Most of that gets absorbed. Visible makes it all the way down. Radio makes it all the way down. Any guesses about why our eyes evolved the way that we did? It'd be kind of a bummer if we had X-ray eyes. You wouldn't be able to see a very long distance, and there would be no source of light to illuminate them. So visible light, there's this nice window, and radio waves actually make it through the atmosphere. So those basically are atmosphere invariant for absorbing the light. There's still the distortion. So even if you make it through the atmosphere is chunky. It's not like a perfect flat piece of glass. So there are hot cells of air that are rising, cold cells of air that are falling. The whole thing is churning all the time. There's 100 kilometers of gas in between you and space, and it's constantly milling about. So what you get is, some fundamental things that you actually wouldn't be able to know. So for instance, this is a binary star, and if you were to image it without the atmosphere in the way, you would be able to clearly identify it as a binary star. But if you smear things out on the order of an arc second, so that's 1/60th of 1/60th of a finger at arm's length, you would have it smeared out to the point where you couldn't even distinguish the two stars as two. It would look like one coherent lump. So this is not fundamental, but it is a problem with the atmosphere, and it basically limits all observations, so you can't see anything to better angular resolution than 1 arc second. So this is totally issue with job number 2. And maybe you want to think about it as this. So this is like a glass, this weird security glass that probably your great aunt has. I don't know why. Went out of favor. Old people love this stuff. But you have this chunky glass, kind of like the atmosphere, and it basically smooshes out the image. And you don't really know exactly where this patch of, white light or red light is coming from. So this is the role of the atmosphere. And that's an issue even if the light makes it through. So you guys have seen this before when, the sun is setting and you start seeing these mirages and distortions. This is because there's just a little bit extra atmosphere because of the line of sight, like really flat. So there's more atmosphere, so you tend to notice the distortion more. So this is sunset being, this is the star in our backyard. How are you ever going to be able to see a star that's really far away? I also like this image because that's the famous green flash. So if you see the sun set over the ocean, it produces this weird green thingy. So bummer. There's a new cool solution to this. I'll leave these here if anybody wants to look at them. The trick is called adaptive optics, and it's two things. Is you actually shine a laser out into the field of view that you're looking at. It's got nothing to do with sending the light to the star. But the laser that you shine out actually interacts with some sodium. There's a little layer of sodium that lives in the upper atmosphere. It makes sodium. It's one of sodium's favorite wavelengths. So sodium starts jiggling and oscillating and absorbing and emitting sodium light. This is at the edge of the atmosphere. So the sodium light the sodium that you've excited travels back to you. You know exactly where you shine the laser. So you know exactly what the atmosphere is doing to distort your image. So you're like, I shined the laser there, but then I see my fake sodium star wobbling around. I can correct for it. Because you can collect light from astronomical images for a long period of time, the way that you have to correct for it is actually by having a flexible mirror with hundreds of little motors and actuators on it, and you literally warp and distort the mirror to correct for the shifting of this image of the star. It's crazy, right? So the person who came up with this did so in the 1930s, and it was so far ahead of the technology. Like, okay, just give me some, hundreds of instantly moving, actuating motors and a flexible mirror that's 5 meters across, and then a laser, which hadn't been invented for, 3 decades, will not have been invented for 3 decades, and we can totally do this. But adaptive optics actually basically corrects for all of the atmosphere at this point. So this is a pre-adaptive optics image of the center of our galaxy. So it's about 27,000 light years away, and this is a corrected adaptive optics image, and that's where the supermassive black hole would be. So you can really see the individual stars and image them, and over the course of the years, you'll be able to see how they shift and move around. So this is a new solution. This is actually kind of exciting. The reason it's got to be mechanical is because the image that you're exposing, so you have the CCD, basically the digital film, that sits there and it collects light for 20, 30 minutes or something like that at most. So what you can't do is take a whole bunch of individual images and then kind of stitch them together, because you just don't have enough information. Yeah. So I remember asking that exact same thing and not believing the answer, but it's really true. Is the easiest solution is to warp and deform the mirror mechanically and just let the light fall where it may lay.
You're just trying to maximize. You can always get that extra.
There's a threshold at which you could not stitch together a whole bunch of images into a corrected, coherent. If somebody gave you a CCD plate and there are 2056 by 2056 pixels, and there were only 5 counts on the plate, there's no way you would be able to take another one that looked like that and be like, oh yeah, those match with those. So yeah, it's weirdly, nonsensically, 1% of me still doesn't believe it, except I know that a lot of smart people have thought about this, is that it's easier to deform the mirror and warp it to collect the light as the light shifts back and forth in the atmosphere. But fake star, lots of mirrors. Both of these are pretty good explanations. Okay, so the other solution is, instead of carefully observing and correcting for the atmosphere, and this is an old solution, is you can get above as much of it as you can possibly get above. And there's more atmosphere lower and less atmosphere higher. So by the time you get to Mount Everest, what is it? You're above 80% of the Earth's atmosphere or something like that. That would be a bit much, even though you do need to acclimate to get to these. So Mauna Kea is about 3,000 meters up, and this is in the Atacama High Desert in Chile. They actually leveled this little tour to put their cluster of telescopes up there. And they're above enough of the atmosphere and in places where the weather is noticeably calm enough where they have less of this problem. So what's the real way of solving this atmosphere problem? Seems so obvious now. To burn the entire atmosphere, with a rocket that is lifting the Hubble Space Telescope up into low Earth orbit. It weirdly took a long time for people to get this. So the delicate mirrors surviving space travel and the fact that it seemed kind of frivolous, and why would you fight to put a 2-meter mirror up into space when you have these wonderful 5-meter telescopes on Earth or something like that. So people had been proposing stuff like this since the 1960s and coming up with detailed plans. The first Hubble one, it had an issue, is that they didn't assemble it right, so it needed a corrective lens, actually, that was installed on a second mission. And then secondly, they cheaped out, and they had this kind of Tetris puzzle piece missing. So you'll notice on the early Hubble images, there's this kind of L-shaped bit missing in the images. But this is, just very weirdly resistant to this idea, and it took decades to get the first one up. But the results were instantaneous. So this is, again, pre-adaptive optics. So this is a really good ground-based image of Saturn. So you can see rings, you can see a little bit of weather. If you really squint, you can see the Cassini gap. This is a Hubble image of Saturn, and the Hubble, so this is what I mean, the description. So the Hubble wide field camera, they basically tell you exactly what it is. It's going to go and decode any of the information. See multiple gaps. You can see a couple of moons. You can see Titan. You can actually see the diffraction ring from light passing through Titan's atmosphere and casting. So there's the umbra and the penumbra from Titan on Saturn itself. So that's not so bad. That's quite an improvement. That's another one of the moons of Saturn. So there's one, and if you're really close or look at it there's another one there. Yeah. So a couple of the Saturnian moons. So this is cool. I don't know. It's like an upgrade for planetary science. This is the real thing that Hubble did, which nothing had the ability to do before. So this is the famous Hubble deep field image. You can tell it's old. There's the missing chunk. My understanding is that they didn't really set out to create this image because nobody knew this would be a thing to see, really. What they wanted to do is just kind of calibrate the telescope, and they pointed it at a dark place. So off towards Taurus, I think, or the Big Dipper, forget which, where it's kind of out of the plane of the galaxy and there's not a lot of stars there. So they pointed it conspicuously at a place where there were no stars, and they just collected light, kind of off and on. You take pictures and then you save them and take more pictures and remove cosmic rays and things like that for 1 million seconds. It's like 11 days or so, about a week and a half. And this is all of the photons you get after a week and a half. So in the absence of atmosphere, you're able to keep, and this thing can constantly be pointed in the same direction. It's not stuck to the surface of Earth, so it can move around and follow whatever, just be constantly pointed away from the sun. Or nearly constantly. This is what you get. So there's a star, there's a star, and everything else is a galaxy. So there are about 2,000 galaxies in this image. Each of them has about maybe 200 billion stars in them. And this is such a small piece of the sky, like maybe a tenth of, so maybe like 15 arc minutes or something like that. I forget offhand. But roughly speaking, if you took one of those little plastic straws for cheap diner coffee, you know what I mean? And you held it at arm's length, it would be one of those. So it'd take about 40 million of these to tile over the entire sky. So there are a lot of stars and a lot of galaxies in the cosmos, and nobody had seen anything like this before. So even with like the best ground-based telescopes, you absolutely can't collect light for a week and a half like this. Something atmospheric would get in your way. So this is really just like a totally eye-opening image. This is to give a sense of the scale, this is the post-cursor to that after they updated the cameras, so you'll see that there's no puzzle piece missing. This is the so-called Hubble Ultra Deep Field. It was basically just like redoing the same thing. And they're zooming in. So you start at the level of galaxies. So you see some galaxies painted on there. And this is a chunk of the sky that you can see about that big. Sunheit. Okay, so star there, and then star there. All of these, so this has about 10,000 galaxies in it. And again, it would take 40 million of these to tile over the entire sky. So as a cosmological instrument, Hubble is, I don't know, it's probably still unparalleled, I think. So now we really believe that we should put telescopes in space. So if you look at this absorption chart, which wavelengths of light would you like to put telescopes in space to address? We're humans and we love visible light. They make the best images, but from a purely scientific view, what's really underrepresented? So, yeah, ultraviolet is terrible, and that's still an issue for technical reasons, X-ray, gamma ray, and infrared. So we've done this, and note that none of these look like telescopes, but they do have the same issues of job number 1, job number 2. So this is the Fermi Telescope. It looks at gamma rays. This is what the universe looks like in gamma rays. There are these things which are, they spin, so they blink maybe 1,000 times to 100 times every second. And this is the plane of the Milky Way galaxy. Every once in a while, for a couple of days, the entire thing would turn red with these gamma ray bursts, which nobody really understands or understood until recently. Here's Chandra, it's X-ray. I'll keep showing you guys Chandra images because they're really, really pretty. You have X-ray, UV, and visible light looking at the sun. Ultraviolet light looking out into the cosmos is a little bit hard for technical reasons. Hubble was so successful, now we have this where, it's pretty easy to at least plan something. So all the parts of the electromagnetic spectrum are up. Microwave, which is really like short radio, there are 2 of them. You don't really need them to see microwave on planet Earth. We actually communicate with microwave radiation because it transmits through the atmosphere so well. But these guys are doing a really precise job of measuring the cosmic microwave background radiation, which we'd like to know a lot about. So we'll talk about that. And really quickly, there are 2 bits of non-light astronomy. One's super interesting and up until September kind of theoretical, is that every once in a while actual matter hits us from interstellar space, and there's a particle detector mounted on the International Space Station and a bank of them that are spread around like Argentina and rooftop detectors in the US that really just look for cosmic rays bashing into us. So that's got nothing to do with light. It's actually material from space. So these are these cosmic ray showers. So they come in and they smack into the atmosphere and they create these large showers. You can actually get a phone app where it detects cosmic rays, apparently, I guess. I haven't really looked into it. And up until February, this slide said maybe during your lifetime we would get gravitational radiation, but that actually happened. So this is the, I think this is the Louisiana one. So this is the LIGO detector in Louisiana. There's another one in Hanford in central Washington. And they're L-shaped interferometers that look for the contraction of space-time itself. And there might be another one which was on the drawing board, but that kind of got cut. And this paper came out in February 11th of this year. On September 14th, 2015, the 2 LIGO detectors observed a transient gravitational wave signal, ... They have confidence that, the chances of it being a freak accident is like 1 in a million. And what it is based on the numerical relativity solution, something we'll talk about in a bit, is 1.4 billion light years away, a 36 solar mass and a 29 solar mass black hole collided. So 2 black holes collided and inspiraled and made a single black hole with 62 times the mass of the sun. If you feel like doing some quick arithmetic, there's a discrepancy. So 3 times the mass of the sun in energy. So remember, it takes a paperclip to destroy a city in mass energy. This is 3 times the mass of the sun in mass energy was radiated away in gravitational waves. So this is the first direct detection of black holes, and the first thing that we got in the gravitational radiation show was a black hole eating another one. So there's a lot of evidence that we're going to get like all sorts of really interesting things. So the non-light astronomy is here and now, and the smelloscope will follow us later. I'll leave this up for people. Somebody asked about cosmic rays and all those crappy blurbs on the images that weren't cleaned up from SOHO. These are 2 things that let you know just how much of a chore it is to make space porn. So this is how you clean off cosmic rays and some pictures of what happens before and after. And then this is how you Photoshop together all of the individual bands of light to make like a pretty galaxy. Okay. So I rushed through that, but thank you. So bring questions on Wednesday.